Today, we are going to be discussing solubility, Ksp, and common ion effect. First of all, let us define the term solubility as this topic that branches out to the two other topics. So, what is solubility? Solubility is the property of a solid, liquid, or gaseous chemical substance called solute to dissolve in a solid, liquid, or gaseous solvent. It is the amount of substance, called the solute, that dissolves in a unit volume of a liquid substance, called the solvent, to form a saturated solution under specified conditions of temperature and pressure. Solubility is expressed usually as moles of solute per 100 grams of solvent. Solubilities range widely from infinitely soluble such as ethanol in water to poorly soluble such as silver chloride in water. However, the term insoluble is often applied to poorly soluble compounds, though strictly speaking, there are very few cases where there is absolutely no material dissolved. Those compounds that are poorly soluble or are insoluble are the focus of the next topics to be presented. The slide now shows a summary of the guidelines on the solubility of common ionic compounds in water. The table is where one can base on to determine whether a specific compound will be soluble or insoluble in water. Now, we proceed to the next topic related to solubility, Ksp. Again, let us define what is Ksp. Ksp, or the solubility product constant, is the simplified equilibrium constant defined for equilibrium between a solid's non-respective ions in a solution. Its value indicates the degree to which a compound dissociates in water. The higher the solubility product constant, the more solubility the compound. The Ksp expression for a salt is the product of the concentration of the ions, with each concentration raised to a power equal to the coefficient of that ion in the balance equation for the solubility equilibrium. So what does this mean? Solubility product constants are used to describe saturated solutions of ionic compounds of relatively low solubility. A saturated solution is in a state of dynamic equilibrium between the dissociated ionic compound and the undissolved solid. Let's suppose we have a compound silver chloride. As for every solution, at equilibrium in given conditions, we can write an expression like the one shown, where the concentration of silver and concentration of Cl represent concentrations of silver plus and Cl negative. And the concentration of silver chloride is a value representing an amount of moles in liter of solid of silver chloride. Since silver chloride is a solid, we know that its activity is 1. Thus, we can cancel it out of the equation, leaving us with the Ksp expression of silver chloride. Let us now have a sample problem on Ksp. Silver chloride AgCl has a Ksp equal to 1.77 times 10 raised to negative 10. Now we have to calculate its molar solubility. We know the dissociation equation and the Ksp expression of silver chloride from the previous slide. Then, we substitute the given Ksp value to the equation. We also substitute a variable for the unknown values that we need to find. As we can see in the chemical equation, there is 1-to-1 ratio between Ag plus and Cl negative. I know this from the coefficients, both 1 of the balanced equation. That means that the concentration of the two ions are equal. We can use the same unknown to represent both. Finally, we isolate X and we can get the answer. The first problem covers compounds that have 1-to-1 ratio between the solid ions of the compound it comes from. What if this is not the case? Let's look at the next example. We will ask the same question as before, but this time using a different compound, which is silver chromate. Silver chromate Ag2Cr4 has a Ksp 1.12 times 10 raised to negative 12. Now calculate its molar solubility. Again, we first write the balance dissociation equation of the compound. We can immediately notice this time that the ratio between the ions is 2:1. Thus, there is a need to square the concentration of the silver ion. Then we substitute the Ksp value. After doing so, in substituting a variable for the unknown values, we will need to consider the ratio once again. It is 2:1 ratio. It means that for every 1 ion of chromate dissolved, there is 2 times silver ions as well. So we will substitute X for chromate and 2X for silver. Note that the whole 2X expression will be squared, not just X. So combining like terms, we get 4x cubed equal to Ksp. And solving for X, we get the value 6.54 times 10 raised to negative 5, which is the molar solubility of chromate. From the previous two problems, we have seen how to solve molar solubilities from Ksp values and balance dissociation equations of compounds. Rewriting the Ksp expression, we can actually write a general form that we can use whenever we write Ksp expressions. The general form of Ksp expressions is concentration of mx raised to m, concentration of ny raised to n, OC raised to O, and so on. Lastly, we have the common effect insolubility. So, it states that in a chemical solution in which several species reversibly associate with each other by an equilibrium process, increasing the concentration of any one of its associated components by adding another chemical that also contains it will cause an increased amount of association. Suppression of ionization of a weak electrolyte by the presence in the same solution with strong electrolyte containing one of the same ions as the weak electrolyte. In solving ion effect problems, it is basically similar to how we solve the usual Ksp problems, except we add an extra step of adding a certain amount to the concentration of one of the ions. Taking for example, calculate the solubility of PbSO4 in 0.1 molar Na2SO4. PbSO4 has a Ksp of 1.96 times 10 raised to negative 8. As we can see, instead of just being pure water, the solvent is sodium sulfate. We know based on the guidance of solubility that all compounds of sodium are soluble, thus it proceeds to complete dissociation. So the solvent here has a 0.1 molar of Na2 plus ions and 0.1 molar of SO4 ions as well. Ksp expression for the compound to be dissolved, we can see that SO4 ions is common to both the solvent and the solute. Therefore, with an increase in the concentration of one of the ions, we should be expecting a lesser molar solubility as I mentioned in the definition. Getting the molar solubility of the compound in water, we can get a value of 1.40 times 10 raised to negative 4. Now, if we add the common ion, instead of just substituting a variable to an unknown amount of an ion, we also add the value of the concentration that is already dissolved in the solvent. Thus, the Ksp expression would look like this. When solving for x, we can get a molar solubility of 1.96 times 10 raised to negative 7, which is surely less than its molar solubility in water. So thank you for watching, guys.